right. Hello everyone, good morning. All right, so what are we going to do today? So I decided to focus our test number 2 only on rational zeros. Okay, so that's what we are going to do today. We are going to continue working with rational zeros. There are 3 main topics that I want to discuss. I already presented those 2 of those 3 topics in our lectures. And today is going to be a day where we are going to see more examples and we are going to practice. Okay, so that's what we are going to do Wednesday and Friday. We are going to get more practice. We are going to be practicing all together. I have selected a few exercises to present to you for today. So I'm going to start working with them, but then I'm going to ask you to start working with all the exercises that I'm going to. The remaining of the exercises, because I want to see how you are getting this material. Okay, as you have seen previously from the previous lectures, yes, this is a condensed topic for our class, where we go through different properties of the polynomials, and sometimes it could get a little abstract. Okay, once we get the step and when we understand what's happening, everything becomes mechanical and very straightforward. But before getting to that part, we need to do a bunch of practice. So that is our focus. Wednesday and Friday is going to be for practicing. Okay. Any question before we start? All right. So in our review, in the review you have all the topics that we intend to cover in 1148 for test number 2. Unfortunately for the time, we are restrained for the short time that we have on summer semester. So in the review you have exercises that covers all those topics, but for our evaluation I'm going only to be focusing on, in the review you can follow the topics that I want to focus on. From a graph of a polynomial, you will write its equation. Okay. So it will be write the polynomial function from its graph using turning points and x-intercepts. Okay, so that is the first topic that I'm going to be evaluating on test number 2. Then we are going to build or construct polynomials with these specific zeros and with this specific point. That is related roots, real zero, factor, and intercept, and analyze multiplicity. Okay. At the end, what we are going to be doing is writing the polynomial function based on their zeros, their multiplicity, and based on the zero and the multiplicity. That leads off to their degree. And the other one that we are going to be focusing on is all these steps where we the exercise gives to us a polynomial. That polynomial will have rational zeros. Okay. We are not going to be working with irrational, neither with complex zeros. And you need to go through all the steps, list all possible zeros, all possible rational zeros, determine the zero of the function, and then factor the function. Okay, so those are the 3 topics that I'm going to be evaluating on the quiz and test number 2. Okay, So you are not going to sketch the graph of a polynomial function. You are going to be focusing on 5.2 from 5.1 related roots and write polynomial function from each graph. We are not going to cover rational functions, and we are not going to cover inequalities. Though you have the material on the review, okay? And you have the material, if you have bought the access to the book, you have that material there. Okay? Unfortunately, we are not going to be able to cover this due to that. Any questions? Okay, so what I said is that we are going to be covering 3 topics, and you need to take that for your project, okay? So you need to be writing what about those 3 topics, okay? How to write a polynomial equation from its graph, how to write a polynomial function from its zeros and multiplicity, and how to identify, how to write a polynomial function from its standard form to its factor form. Between the standard form and the factor form, we go through the properties. List all possible rational zeros, identify the zeros, and then get the factors. And that's what we are going to start with doing in our exercise. So we are going to start with this exercise. Find a polynomial function, find a polynomial f of x of degree 3, okay, that has the following zeros. Okay, so what is the goal of this exercise? Well, we need to write the equation of a polynomial that meets this criteria. The degree is 3 and its zeros are 0, -6, and +1. So how are we going to do that? Step number 1. We are going to take into consideration the zeros okay. Why would I want to start with the zeros? What is the relationship between the zeros of a polynomial function and its factors, the factor of the polynomial? Can anyone tell me the relation between the zeros of a polynomial function and the factor of the polynomial function? How we use the zeros to get the factors of the polynomial functions? Anyone? What is the relationship between the zeros of a polynomial function with the factors of the polynomial function? You are close, you're close. Before we get to the degree, there is something before getting to the degree, and it is the zeros are related with the linear factors, okay, the linear factors of this polynomial. Okay, so how we turned, or how we take the zeros and we then write the linear factor of the polynomial? Well, let's start with the first zero, which is the value of 0. We are going to create a linear factor, so x minus this value, which is 0. We can simplify this as just having x. So that is the linear factor when the 0 of the polynomial has a value of 0. Okay, let's do with 6. Now we start writing this following. We write the parenthesis, x minus, and then we plug in here that value of the 0. In this case, we have negative 6. So we simplify this with x plus 6. Okay? Again, the two parentheses, x minus, and then we take this value and we put it here. We don't need to simplify here further. Okay? Now, Jean, to add to your comment, yeah, the zeros will be also related to the degree, but what property of the 0 is specifically related with the degree of the polynomial is going to be their multiplicity. So right now, the multiplicity of those zeros is not given. Okay? The multiplicity is related, the multiplicity of the 0 is related to the power of the linear factors. Okay? So, we know we need to give a value to each of these zeros, a power to each of these linear factors. Let me put it here, okay? So we need to add, or we need to write a power for each of these factors. That exponent, that power, is related to their multiplicity. The multiplicity, we have two categories. It's going to be even or odd. Now, the actual value of those powers, the actual value of those powers, when we take the sum of those exponent of those powers, what we need to get is the degree of the polynomial. So whatever value we put here for the multiplicity or power of each linear factor, when we add them together, the sum needs to be equal to the degree of the polynomial. Degree is 3. So now I'm going to ask you, what are the possibilities here? For example, if I give the 0 of value of 0 a multiplicity that is odd, and the value of the power of the value of the power is just 1, right? So that means that this linear factor will have a power of 1. What are the other two numbers that we can put here that when we add these three numbers together, we got a value of 3? What possibilities we have? 1 and 1, correct? So 1, there's no more room here. We have 3 linear factors, its degree is 3. The only possibility here is to add a power of 1 to each of these linear factors. So we are getting that their multiplicity of each case here is odd, odd, and odd. This part, the category of the multiplicity here is not so important because we are not working with the graph. Remember that the multiplicity has an effect on the graph behavior on the x-intercept, okay? But just as a reminder, okay, multiplicity and power are related together because the power of the linear factors is directly related to the multiplicity of the zeros, okay? And the multiplicity, or this actual value, what it says is how many times these zeros appears or are part of that polynomial. Okay, so we have only the value of 0 just one time as a 0 of the polynomial. We have the value of -6 just one time as the 0 of the polynomial, and the value of 1 appears just one time as a 0 for the polynomial that we are working with. Okay, so now we are almost done with our work here. This highlighted the highlight part here is what I'm going to take, and I'm going to write then here, and we're going to add them or multiply them together. Okay, so I am creating that equation of that polynomial, but there's something that is missing, and what is missing is the leading coefficient. So here there is no way we can get that value, because the only information that we have is that the degree need to be 3 and the zeros need to be 0, -6, and 1. Okay, so we stop here. This is how we write the equation of a polynomial of degree 3 and that has the zeros of 0, -6, and +1. Okay, we always will add that variable a that represents the leading coefficient. We do not know the actual leading coefficient because right now we have an infinity possibilities of polynomials with these exact properties: a degree of 3 and zeros being 0, -6, and 1. Okay, so that is how we answer this. Any question? Yeah, we are going to do that because that is going to be a separate part of the same exercise. When a given point, when the exercise gives us a point on the graph, then we can identify that leading coefficient. But right now we don't have more information to get that value. All right, let's do a second one. Okay, and I'm going to do this one. I want you to follow me because then we have 2 more, and those 2 more is the one that I want you to try. Okay, and after we do all those 4 examples, then we will do the part where we are going to identify the value of the leading coefficient. Okay, step number 1, what we want to do first here is we know that we need to find a polynomial and with these properties. The degree needs to be 4 and their zeros are 7, -1, and 0. And here we have something that wasn't on the first exercise. -1 has a multiplicity of 2, and we are going to see how this how we need to take into consideration this multiplicity. So let's start with zeros. We are going to do the list of the zeros that we have. We have 7, we have -1, and we have the value of 0. Remember, the zeros of the polynomial are related to the linear factor of the polynomial. And how are we going to write those linear factors? So what we need to do is to plug in here the values that we have as zeros. So x minus 7, x minus -1, careful with the negatives. In this case, we need to simplify. x minus 0. Here we simplify because 0 get cancelled. And then we need to think about what is going to be the power that goes on top of those factors. The multiplicity slash power. From the exercise, we got that the multiplicity of -1 need to be 2. That's given from the exercise. So that is a multiplicity that is given. So that means that we know that this power is 2 here. Okay? But now we need to figure out, or we need to find some numbers that for the multiplicity of the 0, 7 and for the 0, 0. Okay? How are we going to find those values that will meet the property of this polynomial, which is this polynomial need to be a degree of 4. So what will you do in this case? Or what are the possibilities that we have? One, for which 0? X minus 7, okay. So if we put 1 here, these two together makes 3, right? So, and 1 here. When we add these together, we got a value of 4, which is the degree, and we are good with that. Okay. Now, from this table, we have all the information that we need to write our polynomial. So we have the 3 factors. I always like to start, if I have a factor just of x, I always like to start with the factor x, but the order here is not important. So then I will put x minus 7, x plus 2, and remember that x plus 2 has a multiplicity of, this is plus 1. Plus 1. The 0 is -1, so x minus minus 1 is x plus 1. Okay, so x plus 1 has a multiplicity of 2. So we have 3 factors. One of them repeats itself because the power of 2. So when we add those numbers, we got a degree of 4. So this is a degree of 4. And because we don't have further information, we are just going to add an a there, a variable a in front of x, representing the leading coefficient. Okay, any question? Okay, so I'm going to give you a few minutes to now try this one. Let me zoom in. Okay, can you read it well on your end? Perfect. Okay, so let's take a few minutes. Let's do this. I'm going to turn off my webcam. I'm going to I'm going to mute myself. I'm going to give you 3 to 5 minutes to see with what polynomial you got. Okay. Okay, I would like to see your answers on the chat, or if you can just tell me what is your polynomial. You can mute yourself and tell me just your polynomial. Okay, could you repeat this first part? Okay, perfect. Oh, perfect, perfect. That's great. That's great. Gene, I like that. The only thing that you missed, Gene, is the leading coefficient representation with A. Nicole, that looks very good. Okay, perfect. Okay, so correct answer. F of x equals A. We don't have information for those for the leading coefficient. X correspond to the zero value of 0, the 0 of the polynomial equal to 0, then x minus 1, x plus 9, x minus 8, and x minus 5. Okay, okay, perfect. Okay, so see, this is not something complicated. Once we have the zeros, we have the degree, we can create a polynomial. Okay, we need to make sure that we are meeting this requirement. The degree is 5. So this exponent is 1, this exponent is 1, this exponent is 1 as well. 1 and 1. All these together, we got a value of 5. So we have in a degree of 5. Okay? Another one, let's do the first exercise that you have on the review that is about this topic. Okay? This one is interesting. You will see that there is no degree given, but we have a point. Okay? So start working with this one. Again, I'm going to give you I'm going to give you just 3 minutes, okay? And then I will ask you for your final answer, okay? Okay, if you have your answer ready, please put it on the chat, or just tell me your answer. Jacqueline, sorry, you have a question. Go ahead, Jacqueline. Jacqueline, you mute yourself, I cannot hear you. Jacqueline, if you are trying to speak, I cannot hear anything from you. Okay, so let's just one together. We need to find a polynomial function with degree in zeros, right? So let's start with that. We have the zeros. Okay, so we have that 1, 0, 2, and 4. And what we know is that the linear factors are taken from these values. So x plus 1, okay? This is just the simplified version. X minus 2, and x minus 4. So what about their multiplicity or the power? What we know is that the power of the exponents or the multiplicity of the 0 is going to be rated with the degree. But we don't have an actual degree. So in this case, we have freedom to choose whatever we want in terms of their multiplicity. But I want to make things simple, right? If we don't have, if a degree is not given, we are going to make things simple. So the exponent for each linear factor, the power of linear factor is just going to be 1. We don't need to complicate things, okay? So you just put 1 there, and we are for sure meeting the requirement that this polynomial has these exact zeros. Okay, so if we have chosen 1, 1, 1, 1 for each 0, their multiplicity and the power of the exponent. So what degree do we have here? 1, 2, 3, 4. Okay, so we have a degree of 4. This is a degree of 4. Okay, and we have the freedom to choose what degree is because the degree is not given. Okay, now. Any questions so far? So this exercise has something different, and is that a point is given. There is a point for this polynomial. So the degree is not a requirement for a polynomial, but rather a point of this polynomial. With this polynomial, with this point given, then we can find the value of the leading coefficient. And this is how we are going to do it. So the point that we have is 1/2, 63. This means that the x value of this point is 1/2, and then the y value, which is f of x, okay, the value of the function is equal 63. I'm going to erase y because we are working with a function, so we are using the function notation. Okay, so it is interesting because now we have the y value, so the value of the function, and also we have the x value that gives us that specific value. So from this point, we can conclude that when x is 1/2, the value of the function is 63. Okay? And we are going to use this information to identify the value of the leading coefficient. How are we going to do that? So this is correct. That's exactly what we are going to do. Because we have this equation, so what I'm going to do, let me first erase all the x's. So if we plug in 1/2 in the place of x, this is what we have. Okay, and we know that f of 1/2, all this is equal to 63. So I'm going to erase this. I'm just going to put 63. And then what we need to do is to solve for a. So we have our leading coefficient here. Our leading coefficient is a variable. So what we need to do is to solve this equation. Okay? I'm going to give you 4 minutes to find the value of a. Okay? When you finish, please put the value of a on the chat. Okay, so I'm seeing 16, 16, 12, 16, 16. Okay. So 16 is the right answer. Let's see it. Let's see how we solve this. So 63 equals a times 1/2, and then this is going to be 3/2. This is going to be negative 3/2, and then this is going to be negative 7/2. Okay, then we got 63 here, a, and then we multiply all the denominators. We got 2, 4, 8, 16, and then on top we have 1 times 3 is 3, then 3 we have 9, 9 times 7, 63, 2 negative makes a positive. We multiply both sides by the reciprocal of this. We cancel 63, 63, 63, and then what is left is 16 equals a, so we got the value for a, 16. And then what we need to do is to go here to finish our exercise, is to replace a with 16, and that is our polynomial. All right, so those are, we've seen examples of one topic that we are going to cover in test number 2. Okay, zeros are given, degree could be given, or a point on the graph could be given. Okay, and based on those, the information that is given, you will write the equation of the polynomial. Okay, this is the other topic we are going to be working with. We talked about this one in the previous lecture. Let's go and do this example. And what we want to do here with the graph, or from this graph, what we are going to do, this is a continuous and smooth curve. So it could be a graph of a polynomial. It will be a polynomial function or a polynomial graph. Okay, so that's the first thing that we are going to analyze. Okay, so we have a continuous and smooth curve. So then we can write an equation that represents this portion, okay, or that represents this graph with a polynomial function. Okay, this one is important because here is where we are going to take all those properties that we have discussed to, from just the graph, create a polynomial. Okay, so let's start with that. Okay, the first thing that we are seeing is that the end behaviors of the graph are, the left side goes down onto the left side, the right side, or the right endpoint goes up onto the right side. So this shape will tell us about the degree of the polynomial. My question for you is it odd or is it even? The degree of this polynomial is odd or even, based on the shape of the endpoints. Yes, Georgia, is odd. Is odd. When the endpoints, one goes down and one goes up, the degree is odd. We don't actually know the value of the degree, okay? But we know that it's odd. Then, the other thing that we are going to analyze is going to be how many turn. Yeah, let's go to previous class. Okay. The shape of a polynomial graph is determined by three concepts of the polynomial itself: the leading coefficient, the degree, and the multiplicity of the zeros. Okay? When the degree determines the endpoints, the degree and the leading coefficient will determine the endpoints of a polynomial function. When the degree is even, we are going to have a parabola shape. Something is missing here because we are not going to know what's happening in the middle just by the degree and the leading coefficient. But we know that if the degree is even, the graph, the endpoints of the polynomial function will go up, both will go up if the leading coefficient is positive, or they are going to be both down if the leading coefficient is negative. Okay, that is when the degree is even. When the degree is odd, we are going to have something like a cube shape. Well, this is not a cube shape. Something like this. Okay, when the degree is up, we are going to have a cube shape. Okay, remember, degree is even. Remember this with a parabola. And when it's odd, relates the shape of the graph with a cube function. Okay, a parabola or a square function goes up or goes down both ends. A cube function, x to the power of 3, is like a snake going up. Okay, so the only thing that we are not going to be able to determine is going to be what's happening in the middle. But the endpoints, we are going to know that if one goes down to the left and the right endpoint goes up to the right side, means that the degree is odd and the leading coefficient is positive. If otherwise, the left side goes to the left and up and the right side goes down and to the right side, that means that the degree is odd but the leading coefficient is negative. Did I answer your questions? Okay. Jacqueline, I saw your question now. Let me finish with this exercise and then I will go back to your question. Okay. Okay. So that's how we know that degree is odd. The other thing is what is the leading coefficient? Leading coefficient sign. Okay. Leading coefficient sign. Positive or negative? It's positive. Okay, positive because of what we just saw from the table, that if left side goes down the left side and right side goes over to the right side, the leading coefficient sign is positive. Okay. Another important concept is going to be the turning points, where the stream values, the relative stream value happened. Okay, in this case, we have relative stream values here. We have the local maximum and we have the local minimum. But these are very important because these are turning points. So we have two turning points. And then my question is, what is the relation of the turning points and the degree of the polynomial? And we talked about this on the previous class. So take a moment, go to your notes and find what is the relationship between the turning points and the degree of the polynomial, and then tell me what is going to be the relationship here between two turning points and the degree of this polynomial. Okay? How would you describe the degree of this polynomial if we have two turning points? Anyone? Say one more time, Timothy. Okay, that's one possibility, yes, but we need to be, I want first, before we decide what is going to be the actual degree, I want a description of the relationship between two turning points and the degree of this polynomial. Okay. So how are we going to describe this? At least, the important word here is at least degree of 3. Why at least? Our degree could be greater than the number of turning points. Okay? But no, it's not going to be ever equal to the number of turning points or less than the number of turning points. Okay. So at least means that it could be 3, it could be 5, but could it be equal to 8? Could it be 10? Can we have a degree here of 8, of 10, of 12, of 4? What do you think? Only up. Perfect. Thank you, Timothy. We know that it is up. Yes, at least it's going to have a degree of 3. But it could not be 4. It could be 3, 5, 7, 9. Okay? Careful with that. That's okay. Careful with that, because our degree need to meet this condition. It has to be at least one value greater than the number of turning points, but also need to meet the condition of that the degree need to be odd or even, depending on the end points of end behavior of the graph of the polynomial function. All right. Another important property that we can take from the graph is going to be the x-intercept. And why the x-intercept are going to be important? Can anyone tell me why the x-intercept are important? Perfect. So we have three x-intercepts. We have 0, -1, 0. We have +1, 0, and we have 3, 0. From the x-intercept, we can take the zeros. So the zeros are -1, +1, and 3. And from the zeros, we can get the linear factors. So here are x plus 1, x minus 1, and x minus 3. Okay? What about their multiplicity? Can you describe their multiplicity just by looking at the graph? If we decide for the degree to be 3, okay? If we decide for the degree to be 3, so 1, 1, and 1 could be a possible number for the power of each factor. But how would you make sure that you are allowed to use 1, 1, and 1? What you need to consider to make sure that the number that you are selecting for the multiplicity are correct with the graph that we have in screen. Okay, so 1, 1, 1 is correct when we select a degree of 3, but how would you know that the degree of 1 is correct, the exponent of 1 is correct for these linear factors? Okay, let's look at the behavior of the graph at those x-intercepts. We have that at this point the graph cross again here, and cross again here. And this behavior is related to an odd multiplicity. Odd multiplicity and odd multiplicity. So yes, now we can use the value of 1, 1, and 1 for the power of each of our factors. Okay? Careful with this part, okay? Because if we select a degree of 3, okay, we need to make sure that the power that we use for our factors now, when the sum of those numbers is equal to the degree that we have selected, but also they are sound with the behavior of the graph at those x-intercepts. Okay, if for whatever reason one of these 0 was one of those x-intercepts in the graph behavior just touches or bounces at the x-axis, then one of these power needed to be even. Okay, and we are going to see an example where the multiplicity or the behavior of the graph at the x-intercepts is even, to see how this how the behavior of the graph at the x-intercepts determine the actual number of the power of each linear factors. Okay, so yes, you were correct by selecting 1, 1, 1 because the sum of those numbers is equal to 3. But before actually going through commit on those numbers, you need to make sure that the number that you are thinking are sound or are a good fit for the behavior of the graph at the x-intercepts. Okay, by this point we are good to write for writing our polynomial. Still, we don't have a leading coefficient. We know that it's positive, so a, then x plus 1 is power is just 1, so we don't need to add it there or write it here. X minus 1 and x minus 3. Any questions so far here? Okay, so then how are we going to find the value of a? In the previous example, when we were writing the polynomial function based on the zeros and a point, well, we have a point there that we used to determine the value of the leading coefficient. Here in this graph, we can identify those values. Usually, what I do is, if the only thing I have is the graph of the polynomial and I need to write the equation of that polynomial, I will look at first the y-intercepts. This y-intercept here is 0, 3. Okay? That y-intercept is important because it gives me a point. It gives me a coordinate, a value for x and a value for y that I can use to find the value of the leading coefficient. Well, so that is what we are going to do here. So the point that we have is 0,3, and we are going to use that point to identify the value of a, the leading coefficient. So we have 3 equals a times 3. We divide both sides by 3, and we got that the value of a is just 1. So to finish our exercise, we write our equation, and because the value of a is just 1, we can omit it or just put 1 there. And that is the final answer. Okay. Any question? Not all the points on the graph are going to help you. And depending on the polynomial function on the graph, there are certain points that won't help you to identify the leading coefficient value. For example, if the polynomial has an x-intercept and a y-intercept at the origin, you cannot use the origin because you will cancel both sides of the equation. You will get 0 and 0 on both sides. Okay? So in that case, you don't want to use that number. If you ask me if you can use the x-intercept, let's see what happens if we use the x-intercept to identify the leading coefficient. Okay, so I'm going to use here the x-intercept of 1 and 0. Let's see what happens if we use the x-intercept to find the value of a. So we are going to solve for a. We have 0, a. We have 2. We have a factor of 0 here. In this multiplication, there is a 0. What happened with the 0? It makes everything equals to 0. So you don't want to use the x-intercepts to find the value of the leading coefficient, because what you are going to end with is with a 0 on the right side. You are going to cancel the leading coefficient, and there's no way to find that value there. And it makes sense because the x-intercepts are the actual zeros of the polynomial. So it makes sense that you get 0 and 0 on both sides. Any question? Try this one. Let me do something. Let me put 2 notebooks so you can see the steps. You will tell me how well this looks like. What I'm going to give you are, this point is -5 and 0. This point is 0 and 0. This point here is 8 and 7, sorry. 7 and 0. This point here is -1 and 25. Tell me, can you see this? Both windows are good? Okay, Timothy, thank you. Okay, so try the graph that is on the right side. On the left side is the example that we just did. Try to follow these steps. Okay, these are the steps that I want to see on your test. Okay, so try to come up with an equation for the graph on the right side, and yeah, I'm going to give you, in this case, I'm going to give you 5 to 7 minutes. Okay, if you don't finish during that time, that's okay. Okay, 5 to 7 minutes. I'm going to give you. Jacqueline, your question. Maybe we could talk about your question at the end of the class. Okay. Let's focus on this exercise. So let's start first by using the endpoints of this, the behavior of the ends of this graph, okay, to determine if the degree is going to be odd or even. Degree, so we have one goes down, one goes up. That degree is going to be odd or even?
Odd.
Odd. So degree is odd. Leading coefficient sign. Positive or negative?
Positive.
Positive. Perfect. How many turning points?
2.
We have 2 turning points. What is the relationship with the degree of the polynomial?
At least, it should be at least 3.
At least degree is
No less than 3.
Is 3. At least degree is 3. And remember that at least its degree is 3, but the degree is odd, so 3, 5, 7, and so on. Okay, but at least the degree is 3. That's correct. What else do we got? What that is important?
The x-intercepts.
We got the x-intercepts. So we have -5, 0. We have 0, 0, and we have 7, 0. What is the relationship between the x-intercept and the polynomial itself? Why the x-intercepts are important?
So we can find the zeros and the linear factors.
Correct. Zeros and linear factors. So we got zeros are -5, 0, and +7. Linear factor then are going to be x plus 5, x, and then x plus 7, x minus 7. Okay. So then we need to determine their power. To determine their power, we need to take into consideration at least the degree that it is allowed for this graph and the behavior of the x-intercept. So we have that this behavior on all of these cases, the graph crosses the x-axis. So what is the behavior? What category do these x-intercepts? Let me rephrase the question. What is the multiplicity or the multiplicity category, odd or even, for each of these zeros? The multiplicity of the 0, -5, is it even or odd?
Odd.
It is odd because the graph crosses at -5, so odd. What is the rest of the multiplicity of the 0, 0 and the 0, 7? On both cases, the graph crosses, so the multiplicity is odd for both as well. All these zeros has a multiplicity that is odd. So now that we know that the category of the multiplicity, now we can come up with values for the power of each of these 0 of each linear factor, the power of this linear factor. 1, 1, 1, the sum is 3. We keep things simple. 1 is odd, so we have decided that the power of each factor is going to be 1. We start writing our equation for this polynomial, and what is missing here is the leading coefficient. So how are we going to know the leading coefficient? We are going to select a point on the graph that is not an x-intercept. A point on the graph that is not an x-intercept, the one that is given there, is negative 1, 25. Remember, if you use an x-intercept, you will not be able to find the value of a, because you are going to cancel both sides and you are going to have 0 equal to 0. So the point that we are using is negative 1, 25. That means that 25 equals a times negative 1, negative 1 minus 7 times negative 1 plus 5, and we solve this for a. So 25 equals a negative 1 times negative 8 times positive 4. So we have a here. 1 times negative 1 times negative 8 is positive 8. 8 times 4 is 32. We divide both sides by 32. And we got that the value of a is equal to 25 over 32. To finish our exercise, we go to our previously written equation and we replace a with the value that we have found, which is 25 over 32. And that is how we write the polynomial of that graph. Any question? Let's do this one. This one is on the review. If you cannot see it well, let me try to a little bit. Can you read this well? Okay, so let's do this one. Let's take again 5 to 7 minutes. So after that, just tell me your answer and we go over this exercise. Okay. So let's do this one. This one is the one that you have on the review. Okay. Let's start with identifying the degree. Is the degree is going to be odd or even?
Even.
Okay. We got that the degree is going to be even. How do we know that the degree is going to be even? Perfect, correct. Both are facing the same direction, both ends, so the degree is even. Leading coefficient sign. Positive or negative? It is positive, yes. Both ends goes up. The degree is even, both go up, then the leading coefficient is positive. Okay. What else do we need? What else we need to look for? Turning points. How many turning points do we have? How many? We have 3. 1, 2, and 3. 3 turning points. What is the relationship between the turning points and the degree? At least the degree is 4. Okay. Then what else we need to look for here? X-intercept, correct. So we have negative 2, 0, we have positive 1, 0, and we have 3, 0. Okay, so this is related to the zeros, and the zero is related to the linear factors. Okay, so we have negative 2, positive 1, 3, so linear factor is positive 2, minus 1, and x minus 3. Now, so if we decide for the degree to be 4, so multiplicity slash power, now we need to find the value of the exponent of this factor. The first thing, before getting to the actual value of the powers, we need to see the behavior of each x-intercept. So this one, we are seeing this behavior of the graph at the x-intercept of negative 2, 0. So here it bounces, it touches the x-axis. So this means that the multiplicity of negative 2 is even. Here it crosses, it means that here the multiplicity is odd, and here the multiplicity is odd as well. So we know that here the multiplicity is even, then is odd, and then is odd. And what we need to do is to find values for the power of the exponent of each factor that first, when we add them together, we got a value of 4 because that's the degree, but also that makes sense with the category of the multiplicity. So what are those values? 2, 1, 1. Correct. So with that, we are ready to start writing our polynomial function. The power of this factor is 2. Okay, and this is what we got so far. Now, we need to find the value of the leading coefficient. And we have this point here. This point is conveniently a y-intercept. If we have a y-intercept, it's perfect because it's easier because the value of x then is 0. So what we need to do is to substitute x with 0, substitute f of x with 12, and we solve for a. So we have positive 3 here, 12, and the value of a is 1. So we go back here to our initially written equation. We cannot meet the value, we cannot meet the leading coefficient because it's just 1. And that is our final answer. Okay. Any question on how we did this one? Okay. Before we finish our class, we are going to finish with this exercise. This is an example of how to find the zeros and to write the polynomial in the factor form. What I want you to do is please write down this exercise, this polynomial function on your note, okay, because these are some examples that we are going to continue working on Friday, because I want to see you to try this before Friday, okay, because we are going to talk about this one on Friday. Okay, so I'm going to give you 2 minutes or a minute to write down these 3 polynomial functions. Okay, this is exercise. These are exercises for practice. Okay. So we are going to finish with an example on how to solve these exercises. Okay, how to write this polynomial, which is in the standard form, simplified equation, into its factor form, okay, by using the properties of the zeros and the linear factors. Okay. If you are still writing, I'm going to change to the exercise that we are going to do right now. But if you need more time, let me know to go back. Okay. Okay, so don't worry, the instruction of this is a screenshot of previous exercise that I have previously worked on previous class. So don't worry too much about the instruction, because the instruction only says find all the zeros of the function. But I want you to go further, and I want you to write the function in a standard form. Okay, so the objective of this exercise is to write the function in a standard form. Step number 1 is to find all possible rational zeros. Okay, and for doing that, we need to find the factor of the constant value, which is 5, and the factor of the leading coefficient, which is 6, Okay, with this, then we need to create the possible list, the possible rational zeros list, and we are going to do that by combining these numbers. Okay, so 1 over 1 is just plus minus 1. 5 over 1 is plus minus 5. Then we do 1 over 2 plus minus 1 half. 1 over 3 plus minus 1 third. 1 over 6 plus minus 1 over 6. And then we repeat the same process with 5 plus minus 5 over the question. Are you talking about this one, which one? The first one. Okay, so 1 over 1, that gives me 1. Did I answer your question? Okay. Okay. Factor of 5. Let's start with factor of 5. 1 times 5 is 5. So that is 1 is a factor. Okay. 1 times 6, those are factor of 6. That's how we get 1 in these sets. Okay. 2 and 3 are here because we can make 6 when we multiply 2 times 3. Okay, all the numbers that we multiply together and we got those values are going to be part of our list. Okay, so 5 over 2, then 5 over 3, plus minus 5 over 3, and then 5 over 6. I think I got everyone here. Yeah. Okay. So that's the list. Do not forget the plus and minus. Okay. All right. So this is 1 over 6. All right. So that is step number 1. We have identified the list of possible rational zeros. All these numbers are not necessarily the zeros of the polynomial, but they are the possible rational zeros. Okay. Step number 2, we need to identify the first zero. Okay. And for that, what we're going to do is to do the graph evaluation. I'm gonna skip that part because we don't have too much time to finish this exercise. So x equals minus 5 is 1 0 of the polynomial. Okay. Step number 3, we got a linear factor from that 0. So the linear factor is x plus 5. Then step number 4 is when we are going to divide 6 x cubed plus 31 x squared plus 4 minus 5. Plus 4x minus 5. So we are going to divide the polynomial by this factor. Okay, because the dividend, the factor that the factor of the polynomial is a linear factor. We can do synthetic division. 6, 3, 1, 4 and minus 5. We do synthetic division. We go down, we add, we go up, we multiply. And this guy here is what we want, because that 0 there is telling us that indeed negative 5 is a 0 of the polynomial. From here, we got the depressed equation. In this case, it's going to be a quadratic equation because we started with a degree of 3 polynomial. Okay, and once we arrive to a degree of 2, what we are going to do is to find the 2 remainder zeros that are part of this quadratic equation. Okay, if they are real zeros. Sometimes they are not going to be real zeros, but this one is going to give us real zeros, because the leading coefficient of this polynomial of degree of 2 is different than 1. I'm not going to bother with FOIL. Yes, you can do FOIL, but let's go, don't waste time on trying to find those numbers that fit with the FOIL method. Let's do just the quadratic formula. The quadratic formula here is going to be negative 1 plus 1 minus 1 squared minus 4 times 6 times negative 1. All this divided by 2 times 6. And then we solve the formula. So minus 1 plus minus 1 minus, this is 2 negative is positive. So 4 times 6 is 24. 2 times 6 is 12. Okay, so we have negative 1 here, plus and minus. This is 21 plus 24, 25. Square root of 25 is 5. All this over 12. And here, from here, we got 2 values when we add and when we subtract. When we subtract, we got 4 over 12, which is positive 1/3. When we subtract, we got negative 6 over 12, which is negative 1/2. Okay, so those are the zeros. So the zero that we got starting from negative 5. Negative 5, we taken negative 5 from the original polynomial degree of 3. Then from the degree of 2, we got 1 over 3. And then we got negative 1 over 2. So the factor, to write the in factor form the polynomial, the leading coefficient was 6, then x plus 5, then x minus 3, then x plus 1/2. And that is the factor form of the polynomial that we started with. So you have 3 exercises. Please practice those exercises before Friday, so because we are going to continue working on these exercises. Is 10:55. Thank you so much for being here. Jacqueline, I have a question for you. You have a question for me. I'm going to work with your question. If you have if any one of you have a question, you can stay. If not, have a great rest of the day. I will see you on Friday.